Okay, so hello everyone. My name is Han Xiao. I run the model training and inference team at Elastic. In my last talk, I spoke about test-time compute for search, and I said search is all about test-time compute because you kind of spend the compute at test time to build relevance by building up a pipeline which composed of embeddings, re-ranker, hybrid search, filtering, and so on. So today I want to push that idea one step further to unlock new capabilities, image tagging. So I will show you how to use a frozen embedding model, in particular jina-embedding v5-omni model, to tag images purely at test time. So let me show you what I want to achieve here. So these are real photos from my Mac studio. They're landscape from San Jose, price tag from Costco, my teammate Felix, and my SSD drive. So nothing really cherry picked here. So under each photo, we have five tags. Those come from V5 Omni models. There's no training anywhere in this pipeline. It is purely test-time compute. And so this is what you are able to build by the end of this talk. So let me state the problem clearly. So we have this Gina embedding V5 Omni model, which is like a multimodal embedding that has 1 billion parameters, image tags in one space. So you probably could use other multimodal here, multimodal embedding model here, but I will not use clip model because of the modality gap. I never tested, but I don't think it will work. I chose V5 Omni mostly because, first of all, it is our model. Secondly, because I use it every day, so I kind of familiar with its vibe. And the question here is, with one image goes in, we want multi-labels back, right? And open vocabulary, not a small predefined set. And there are also some constraints. We don't want any training. We don't want any tagger, like a part of speech tagger. We don't want to build a classifier on top of it. And the model is completely fixed. And all we might do is to spend compute at test time. So a quick recap of what test time compute is, especially for a frozen embedding model. What does that mean? So there are only three families. Family A deeper pass. You run one pass, but you carry more out of it. Each patch, like for example, in Colbert model, each token has a vector. So in the end, you do maxim over multiple vectors. Family B is more passes. So you run the same encoder again and again on multiple views. For example, you can split the document in the text context. You can split the document and embed each sentence or embed each chunk, or crop the image and re-encode each crops. Family C is a calibration. So you work on the vectors that you already have using their statistic, like widening, graph propagation, belief propagation, all this kind of thing. So if you are interested in testing on compute on embedding models, please feel free to scan the QR code in the corner from my last talk. So there are two questions I want to answer. First, can a frozen embedding model become an image tagger by test-time compute alone? No training, no fine-tuning, no head, no classifier. And second, if it can, which of the three test-time scaling is most effective? Deeper pass, small passes, or calibration? Now let me open up the model. The blue block is the Gina embedding V5. It stays frozen. So inside this, there's a vision tower, there's a tech tower trained together. Uh, and three things to notice. First, when an image goes in, the vision tower breaks it into patches, and each patch comes out as its own vector. So this is the capital B. Second, you also get a one put vector for the whole image from the last token. So this is basically how the standard usage of the V5 Omni model. So that's small g. And third is the text bus is the same tower. We push all the like 120,000 tokens through it once offline and cache it as a label matrix E. So PGE, we will use all three in the pipeline. So here's the complete workflow. The top line only run once. We encode the vocabulary into label matrix E. There's like 128,000 tokens. And we estimate the background prior mu from the neutral images. And we filter the vocabulary down about 25,000 real words. The bottom line runs for every image. One forward pass gives the patches, and the global vector, we score them against the label matrix, subtract the mean, deduct, and the top K text comes out. So we can also crop the image and send the crops through the same pipeline multiple times. So that's basically the family B of test time scaling. let's look at step by step. So first, how is a label matrix built? So we feed the tokens one by one through the model as text. You might think that you can just read the input embedding table, but that is not the output space, right? So every token has to go through the tower. That is what puts the tables in the same space as the image. The second step is where do you look in the image? On the left, we have one global vector against each label. So this is usually dominated by the largest object in the image. On the right, we what we do instead is like every patch score against every label, and each label keeps its strongest patch. And it is almost free because those patch vectors already come out of the forward pass. The third step is to remove bias. So every label carries a prior. Some words sit very close to almost every image and the embedding space, just because how the model was trained. So we take the neutral image and random backgrounds with ordinary photos and compute the similarity once and use it as a background prior. At test time, we'll just subtract it. And word that scores high, everything basically goes back to zero. The fourth step is clean up the input. So the tokenizer already knows where the word starts. So we keep only the word tokens that begins a new word, and we drop the fragments. That takes like 100,000 tokens down to 25,000. Then we deduct. We work down the ranking by dropping the word too close in the embedding space and to something that we already kept, like a cat, kitten, cats collapse into one word kitty. No dictionary needed, and the similarity is computed based on the embedding model itself. So now probably the most interesting part is instead of just sending the image once, we can also do manual splitting, like a cropping. Here, there is an example where you do like a 14 crops following the tech leap idea from Triple AI 2024, and all through the same frozen embedding. So each crop is a new image. It gets repatched, scored against every label, and we take the maximum per label across crops. This is the score function for each label in our image tagging pipeline. So we have three terms here. The first is the global vector against the label minus its prior. And the second one is the patch evidence max over patches minus its prior. That is basically the deeper path, the family A of test time scaling. And notice it's recursive, so it calls the same score function on each crop. That is type B test time scaling, right? More passes. But overall, we don't train anything. There's no head, no logis, no learned threshold. So here's a visualization of how the scores look like. Like first, we have the raw score. It's very smooth spell. And then we subtract the prior. What is left on the right is the evidence. Then the word gate, deduct, and finally the top text falls out. And all of this is just label, matrix mass. We benchmark it over Coco 150 data set. And uh, we can see that global pooling gives you some baseline, but multi-crop, this gives you 81% precision one, right? And MAP 7.1. So it is like the most effective test time scaling. We already see that family A and family B both clearly works, which makes me very curious about family C, this calibration thing. The idea here is you already have the vectors, and can you exploit their geometry to get more? The answer is no. Some barely move, some collapse completely. So this is the summary of that experiment. Calibration simply doesn't help on, like, at least on V5 Omni model. So I feel like the reason is that this calibration method was designed for weakly calibrated, like single label two tower clip model. And remember, I said there is a modality gap there. In V5 Omni model, the space is already aligned, is already calibrated, and is already multi-label. So there's nothing left to recover. So here's probably the most important plot in this talk. On the x-axis, we have the time you spend per image. On the y-axis, it's accuracy. And you can see it very clearly that the more compute you spend at test time, the better accuracy it gets. Not every method, of course, but along the parallel front, it holds. More patches and then more crops. So there is a scaling law here for image tagging on further embedding model. And the pink point are basically the family C, the calibration measure. They are very cheap, but they buy you nothing. Remember, overall, we never trained anything, right? Everything fixed, we never trained, we just spend more time in the test time. Okay, so one final question left. Every tag so far is just a single word, like a kitty, cozy, sofa, all this kind of thing, a single word. But I often want a noun phrase, which sometimes tells me more about the image. So how can we get grounded modifiers with no part of speech tagger? Like no grammar, no decoder model, just more compute on the frozen encoder. Well, it turns out we can by borrowing some ideas from Beam Search. We start from the known and expand it. Each candidate's words fills a slot, and we score the whole phrase against its region. We keep the best four, and then we expand all four again, and keep the best four of everything that comes back. So we stop when the phrase is long enough. And it holds up outside the benchmark. So on real photos, those are like probably the photos I took from SML like conference. There are four modes, top five each, and zero annotation, open vocabulary, all from the embedding models alone. Nothing cherry picked. To place this work against the literature, we can see like a tag clip and PIA are training free, but they assume the label is given. The line trains on curated tag lists, and alter is a calibration measure. I think what is unique here is the combination. So first of all, we are training free. We have no pre-trained, predefined label space, and the tokenizer vocabulary is basically the label space. And there is no second model, so everything comes from going deeper on one passes or running more multiple passes. And this is not just a case study. I actually implement this algorithm in Omni. This is a macOS app for local file search using jina-v5-omni model. And it is complete air gap, no network, written in Swift and MRX, highly optimized. So if you're interested in Omni macOS, please scan the QR code on the top right corner. And it's not only for images, the same label matrix and the same scoring rule. You can use it for like video, scan PDF as well. So to summarize, in my last talk, I spent test time compute to buy relevance in search. And in this talk, I spent it to unlock new capabilities. And I think it is fair to call it new because people do not usually connect embedding model with image tagging. And I think there's a lot of left here. For example, how far can we go without training the model by just building pipelines and test time? So I think it's a very interesting direction, especially in the era of agentic search. So the code and benchmark are all here on GitHub. And if you found this interesting, feel free to ping me on X or LinkedIn. And I'm open to any questions. Thanks for your attention.